hospital. Awesome docs out there who really managed to go on under extremely difficult circumstances. I landed up being a part of this international consortium called N95 decontamination of N95 masks, and that was a great learning experience. And everybody in the world started sending us masks to test. So I learned a lot from that. So every culture has had masks. Masks have been around with us for years, like thousands of years. The Inuit used them to protect themselves from the glare of the sun, of the ice, and the snow. People use them in all cultures for dances, for disguise, for whatever else, and for protection. Now, in the plague, when the plague was happening, the plague doctor used to wear a mask like this, and they put some nice smelling stuff over there. They didn't know what was the plague. They just thought maybe if it smells good, it will be better, so they had a mask. Today, of course, we wear masks, whether it's a fancy mask or a dupatta tied around or a handkerchief tied around your thing. Everybody was wearing masks during the pandemic. Now, there are many different types of masks available. There are these kind of masks, there are cloth masks, right? There are these little elastic one on the ear masks, surgical masks. What's the difference between all these masks? Okay, and there are two basic types of masks. There are what are called N95 masks, which are these guys. Okay, and there are surgical masks, which are these guys. Okay. Now the difference is this one fits on your ears. There is a gap at the side. It's designed to be loose. Filter stuff coming in. Your exhalation goes out towards the back. This is mainly to protect. A doctor is chopping up somebody on an operation table. You don't want your spit or something to go there. You don't want a splash from there to come on your face. This is the thing. It is not meant to seal tightly on your face. The N95 mask seals tightly on your face. It filters air both in and out. Okay. This is meant for large droplets. This is meant for small. What we will come to, we will look at what is small and large in a bit. Okay. So first thing, what does mask do? Okay. Just in case you didn't know, the N in an N95 just comes from some historical terminology, means it's not oil resistant. Okay. And 95 is it filters 95% of particles at or larger than 0.3 microns, 300 nanometers. Please remember this length scale, 300 nanometers. Okay, 0.3 microns. Now, if you want a mask, what do you want? You want something that keeps the stuff that you don't want to breathe out, but you want to breathe air. A stainless steel vati has 100% efficiency. If you put it over your mouth, nothing will go through it, but you won't be able to breathe. So there's always a trade-off between breathability and filtration efficiency. This is something which is inherent in a mask design, breathability versus something you don't want to make it too difficult to breathe. If it is too difficult to breathe, people will remove the mask. Okay? Similarly, comfort. If you're like me and you wear glasses and your glasses keep fogging up because of your mask, you will tend to not wear it. If you have to wear a mask for 8 hours and your ears are going to hurt, you're not going to wear it. Okay? So these things may not sound very important, but they land out to be the most important factors in deciding whether people use masks or not. And finally, it has to fit well. You don't want these leaks at the side if you want a mask which is actually going to filter everything. Now, filtration is something, this is straight from the CBSE 6 standard book. The CBSE 6 standard book tells you how to filter. You have people on a construction site who are filtering their sand through a sieve over here. You can separate tea leaves through a strainer, or if you are separating kida from your grain, you can take them out one by one, or stones or whatever else. This is what you filter. Okay, this is the basics of it. And right now there is something in the air. You have a filter. You want to selectively remove some part of it. That's what we are trying to do. Now, everything depends on size. Okay, so you need to know what is the size of particles that I want to keep out. So you have things like pollen grains in summer, and something, there are a lot of pollen grains around which give you asthma or something, it might irritate you. Those are about 10 microns and bigger. Spores of fungi, algae, these are micron size. Bacteria go all the way from this 300 nanometers to 10 microns. Viruses are much smaller, typically hundreds of nanometers. Okay, and of course these things can break up into smaller fragments which could be any size. However, please remember that the chance that a single viral particle is flying around and coming is very low. Mostly, especially for things like COVID, if somebody is coughing or something, the virus is most likely in a cough droplet. Okay, so you have to worry about the droplet, not necessarily the virus size. Okay, now just remember that. So what happens when you cough? How do you generate these cough droplets? Okay, now let's look at it. What happens? Your throat, your passages, they have a lining of mucus. Something irritates it. There is a particle that comes from outside, and that's going to get irritated and going to try and trigger it. Your body wants to throw it out. So what does your body do? Your diaphragm suddenly contracts up. You have a gust of air, and this particle gets hopefully thrown out. At this moment, this gust of air also disturbs this mucous membrane, and it breaks up this mucous membrane and tries and throws some particles of that also go out. Now this is related to basic fluid instabilities. If you have a layer of a fluid, which is in this case your mucus, which has a high viscosity, you have air flowing out over it, low viscosity fluid. If this fluid is flowing fast, this layer is going to get wavy. And beyond a critical thing, this layer is going to break up and shed particles in what is called a Kelvin-Helmholtz instability. Don't worry about it right now. But basically, this is fluid mechanics happening inside your throat, that this layer gets broken up. This is an animation from Wikipedia showing that once the fluid flows something, this thing breaks up and gives you these particles which will flow off. What is interesting is the physics of this is the same at many scales. You see this Kelvin-Helmholtz instability in cloud patterns in the sky. Some days back, or some months back actually, we had the strongest solar flare from the sun, which came and was supposed to knock out communications and all. If you looked at this was a news report, if you looked at the shape of what happens when the solar wind interacts with the Earth's magnetosphere, you also get exactly the same kind of this Kelvin-Helmholtz instabilities over here. So whether it is fluid in your throat, whether it is clouds, whether it is the Earth's magnetosphere, physics, one of the nice things about physics is you can use very simple arguments at different length scales. Okay? Alright, enough of physics for now. Now you have to worry about, I want to do filtering. Let's get back to filtering. I have different, so there is the number of droplets versus the size distribution. Of course, it depends whether you're coughing, breathing, running, depending on that, the distribution changes. But we have some distribution that we want to filter. Okay. Now, the basic filtering mechanism, which is have a sieve, and I will stop some particles which is bigger than the opening in the sieve. Just look at it a bit carefully. Okay. Remember that if you have a sieve like this, which has an opening of this sort, you will allow this guy through, you will allow this guy through. If a particle is bigger than this, and remember we physicists, we love our spherical curves and we love our spherical approximations and everything else, okay, this guy will get stuck. But if you have another particle which is like this, it depends on whether if it's coming this way, it gets stuck, but this guy will go through. So it also depends on the aspect ratio of the particle. Okay, so this thing works if you just say that it's going to block everything bigger than this, you have to define what is bigger and how and whatever else. So, but thankfully, it's a little easier than having to worry, oh god, there are all particles which can go through this. Because what happens? All these masks are made of fibers, molecules come, get stuck on them, there will be some rate at which they get stuck, there will also be some rate at which they dissolve. So you have to worry about the balance between the two. Now, there are many ways you can get particles stuck onto your mask. One is that it just comes and hits the fiber. This is like a goalkeeper stopping a ball. The ball comes, the goalkeeper stops it. This is what you call just inertial impaction. Okay. Now you have, no, that is just direct impaction. Now you have also the fact that these particles are going along the streamlines of the air. Some of them are heavier than things. They may not be able to follow the streamline. So like a car skidding on a bend, it might just go out and hit a fiber. Okay. Then you also have these particles there's always diffusion. And if you have diffusion, there is a chance, like this guy running into the pole, that somebody is randomly moving around will hit a fiber. So because of all this, effectively an opening of this size can actually, these particles appear as if they are bigger than that. Because of these mechanisms, you actually trap particles bigger than the opening size, which is good for you. The best way to make it better is you add an electric field. The same electric field in Chandigarh is dry enough that in winter if you comb your hair you can get sparks, so you take your t-shirt off, you'll get sparks. You can use electrostatics to attract particles. And it doesn't matter if the particles are not charged, because even if you have a neutral particle which is a droplet, that droplet in an electric field will get polarized and hence get attracted. So charge is what is really critical in these masks. Okay? And the key thing is, if you have large particles, just this sieving is enough. You can trap them. But once your particles are small, the only thing that is going to work is charge. And this is the critical difference in an N95 mask versus any other mask. So an N95 mask, and I'm going to pass around right now an N95. So this is the stuff from which an N95 mask is made. Okay, they make it like this. There are multiple layers of cloth. Of cloth and different materials. This very soft material in the middle is polypropylene fibers which are charged. Okay, right now they may not be charged anymore, but this is the layer which had the charge. Okay, you can pass this around. This is from I went and visited a mask making company to see how it is. Please don't peel it over there. Generally, will shed a lot of things. Okay, so the idea is in this mask, the layer in the middle has electrostatic charge, and that is what is really trapping the very fine particles without necessarily. If you made a sieve which was 300 nanometer spacing, it would work, but you won't be able to breathe through it. The pressure differential will be too bad, too big. So you make something which has micron-sized openings, but traps 0.3 micron particles because it's charged. I'll show you some pictures of these as well. And so this charge, and this is why you can't just wash a mask or dip it in, your hand sanitizer or something. The alcohol, the water, whatever it will remove the charge, and then it is no longer an N95. Okay, so that's where the problem is. So now, how does the government qualify this? In most places, including India, a surgical mask needs to be qualified by what is called a BFE, a bacterial filtration efficiency, which is 95% at 3 micron size. And N95 is 95% at 0.3 micron size. And this is something which, during the pandemic, every Tom, Dick and Harry was making masks, sending it to Citra, which is a textile research place in Bangalore, which can only measure this, and saying, 95% hai, chalo N95. Now this is filtration efficiency. Remember, filtration efficiency is useless if the mask is here. Right? Or if it's so loose that it doesn't fit. Okay, this is a very dirty mask. Lockdown, April 2020, I thought I will, have some peace. I get a phone call from Tata Memorial Hospital saying that, look, we have 1 week stock of masks left, do something. Help us somehow. And I said, chalo, let's try. And see, the virologists, medical people, they know how to zap the bug. They know how to decontaminate a virus. You can use radiation, you can use chlorine, you can use hydrogen peroxide, you can use a lot of things. But how do you know that whatever you do, you can autoclave it, you can just heat it up to 120 degrees or something. How do you know that that hasn't damaged the filtration efficiency of your mask? That is the physics problem, right? So for this, you need to measure filtration efficiency. Nobody has a mask tester. Mask testers are made in the US. At that point, even if you had 20 lakhs to buy a mask tester, you couldn't have got it. So what do you do? Because without a mask tester, you don't know whether that process is killing your mask or not. So how do you measure filtration efficiency? The way you measure filtration efficiency, the easiest way is you have air in the ambient, you suck that air through a filter, and you put something which can count how many particles of different sizes are there in the air. You do this, and you measure how many particles are going through this thing. And you can figure out the efficiency of the mask is 1 minus n mask by n ambient, that gives you the efficiency. So the idea is I need a particle counter. And luckily, thanks to the fact that, hey, I'll give you the slides, don't bother taking pictures. You can take all my slides. They're anywhere recorded. I can take pictures of almost of you, but just enjoy it. Luckily, thanks to everybody being worried about air pollution and air quality index, you see PM 2.5, PM 10. What are these numbers? These are numbers of 10 micron and 2.5 micron particles in the air. All these AQI sensors have a little chip inside them, chip meaning a little device of this size, which measures this particle count. Some of these actually have a 0.3 micron channel. They don't tell you PM 0.3, but they have this ability to measure 0.3 micron. So this is a very interesting thing of how I managed to get my hand on this. Ask me later, it's a fun story. Initially, we were trying to do basic experiments in the lab. This is 10th of April. We are trying to use a helium neon laser. We are doing some light scattering experiments and trying to see. You basically use light scattering. Even that chip has a little laser inside. It does light scattering. Okay. Just remember, this is not the blue color of the sky Rayleigh scattering. This is me scattering. Okay. Then eventually we sort of got this sensor and we made it into a dabba like this. And then finally we had a better product. Having cut something out of plastic and made something with the sensor being, this is the dabba, the AQI sensor. This is during the hard lockdown. This is balls stolen from my daughter's toys. We don't have a mannequin on which you put the face mask for testing as a commercial setup would be. We use a ball, we just put a mask and we have some, there's a screw over here and we just tie the strap on it and we put sellotape around this whole thing. You can see the tape here also. Okay, so this is how you make a mask test. But we thought we would actually do it. So the idea is this, let me just explain. We have a ball which has a pipe going through it. This goes through a flow meter because you want to do it at approximately human breathing rates. Okay, and this goes to this chip which is measuring particle counts. The chip is connected to a vacuum pump, and this is our setup. We called it the Mask Integrity Test Resource. You need to very cool titles to your things, otherwise nobody takes it. So this is called Mitra. Right? So and this is 20K for all the components put together. It's 20K, not 20 lakhs. Okay. And the best part of it is Mumbai air, I'm sure Chandigarh air will work, is so dirty that there's enough of 0.3 micron particles. No doubt of it, no problem. We could just use room air. After 6 months of the pandemic, the air started getting so clean that we were dropping, we had to integrate over 5 minutes, 7 minutes to get enough data. Then we decided this is a problem. So then I was working in the hospital. I went and stole some bags of saline and a nebulizer. Okay, and we just used a nebulizer and saline water in the nebulizer and just generated sodium chloride particles in the room. Because that's the only way you could artificially create enough dust in the room so that we could make measurements in 1 minute or something. Because otherwise you're integrating over a very long time. Okay, how does this chip look? We wanted to make it as simple as possible. So this is a typical, you can see the size is a typical plastic dabba like this. There are two dabbas. One contains this little chip that is measuring the air comes in here. We have to make sure the separator is very important that goes through the chip and out. Otherwise, if you suck it, it will just go straight avoiding the chip. And we have a little Arduino kind of thing, which is a Wi-Fi connected thing to get the data out of it. And this works very well. We made a very simple interface so that anybody could just look at the number. This is the number of particles as a function of time. You see, this is where my mask is not there. There's a room air. Through the mask, there are very few particles. Again, when you remove the mask, it's something. So you can just define this is the area of your mask, this is the outside area, and it will calculate it. So this is a very simple interface to use. This is N ambient, this is N mask. You can calculate it. Now, TIFR was very happy. Arey chalo patent karo, kuch to karo, this is good stuff, this is something. We said, look, this is the middle of the pandemic. This is not the time to patent things, and anyway patenting to DAE takes years. So what we did is we put everything on GitHub. All the drawings, all the things, everything is on GitHub, it's open source, and people in the US, people in other places have, we've given them whatever help they needed to make it at this point. So everything is on GitHub, you can look at it. Now once you have a mask tester, of course our main aim is I need the mask tester because I have to figure out how to decontaminate masks, right? But you can do a lot of other things. You can, measure masks, you can do some cool experiments. We helped many groups develop masks. We got some money from DST to make a startup and this, that, well, we helped a startup. We didn't get money. But the main point of the story is we want to decontaminate, okay? So what is the best way to decontaminate and reuse? And remember, I want to zap the bugs, but I don't want to change efficiency. Okay? So what do? Now, these masks, if you look at the thing, these masks were invented by 3M. Okay? These masks were not designed for COVID. These masks were mainly meant for people scraping walls, in a rusty environment, people in mines, people around the place, whatever, where you have to filter out small particles, and they are meant for single use. Why are they meant for single use? Because otherwise I can't sell you good masks. Okay? I will tell you, from my reading of whatever has happened, 3M and other companies knew very well how long these masks will be used, if they could be recycled, if they could reuse, but it wouldn't help them sell masks. Okay, until now, when a lot of these things came. Now, We are decontaminating, we are not sterilizing. In the medical terminology, there is a difference between the two. If I can remove 99.9% of the pathogens, what is called a 3-log reduction, that is decontamination. Sterilization means 99.999, 5-log reduction. Okay? We are interested in decontamination, not in sterilization. You can sterilize also, you just need longer treatment times. But that is enough. The most important thing is, whatever you do should not impact not just the filtration efficiency, but the fit. Okay? And I will tell you that most masks will, this is a perfectly good mask. Okay? Its filtration efficiency is very good, but the strap comes off and then you have to do some jugaad to try and wear your mask. Okay? You are not limited usually by the material of the mask. You are limited by the fact that, for example, in this one, the nose strap has gone off. Okay? So, I mean, you are limited by the fact that it doesn't seal against your face anymore. And if it doesn't seal, it's no good as a mask. So material is not the limitation, straps and the rim deformation is something. And there were lots of, contradictory things. Everybody was trying out different things. So thankfully this N95decon.org was a very good group that I could join and work with them. So we know what doesn't work. Alcohol, disinfectant, soap, water, detergents, all of these will remove the charge. Similarly, bleach solution also will remove the charge. Also, I don't think you want to have a residue of bleach which can give you chlorine or something on your mask. Okay. Ethylene oxide is a standard thing for sterilizing. All your needles and all these things are sterilized with ETO, you see on the package. Ethylene oxide is way too toxic. You don't want the chance of any residue having there on your mask. Gamma ray irradiation, another standard way. And in fact, that is why I think they called us, because DAE, we are part of Department of Atomic Energy. Atomic Energy believes that radiation is a solution for everything. Mangoes ko irradiate karo, onions ko irradiate karo, so mask ko irradiate karo. Right? Now the thing is this, if you've seen a mask going around, that fluffy stuff is polypropylene fibers. Any polymer, you give it UV radiation, it's going to degrade. Your plastic bag, you keep it out in the sun, it becomes brittle after a while. So the problem with putting it in radiation is that you degrade the polymer. So you can't use gamma ray radiation. And you can't use sunlight and the tanning lamps kind of UVA. You can use UVC. Short wavelength UV will kill or whatever, damage the DNA or disrupt the virus. You can't kill a virus, it's not living. But the standard sunlight doesn't do very much to it, there's no UVC in it. So what works? Hydrogen peroxide vapor works very well. There are some companies who have commercial systems which are one room size thing where they spray hydrogen peroxide vapor on 1,000 masks together and all. But that's something which is a large scale process. The easiest thing finally we discovered is time. Right? People, by the time it was almost December 2020, there were enough studies that the SARS-CoV-2 virus does not survive on any surface for more than about 96 hours. So the simplest procedure, this of course requires you to have a stock of masks initially, is you buy 5 masks or 6 masks, one emergency. Use mask 1 on Monday, mask 2 on Tuesday, mask 3 on something. On the 6th day you use mask 1 again. Only thing is you have to be careful that you store the mask correctly, not in a sealed environment, because the mask gets humid. If you leave a humid mask in a sealed thing, you get fungus on it in no time. Okay. Heat and humidity is the other solution, which is what we developed, and also UVC works. Autoclaving, 120 degrees, etc. is above the glass transition temperature of some of these polymers, so it can damage the mask. Liquid H2O2, some people have tried, but it's kind of very corrosive and not good. So I got to work. I said, chalo, let's use heat. Heat is something we can heat stuff anywhere. So I am a scientist. I'm in the lab at TIFR. So I am sticking on temperature sensors to masks, putting them in an oven, measuring temperature, measuring humidity, taking data, what it is like, and doing this. Let's not skip through all this. Does it work? So this is the filtration efficiency. Now I have my mask tester, right? I can measure filtration efficiency. I'm a good scientist. I repeat my stuff. I have error bars in my data. So N95 masks, 2 different brands. Yes, I can do 5 cycles, no problem. Even these surgical masks, even these masks, I can do. There are different types. We'll go through the difference between what is a 10 rupee mask versus a 3 rupee mask if you want. There are different rates, but nothing happens to them. You can heat it up, nothing happens to them. Okay, their efficiency is almost the same. So this works. Now I have to set it up at the hospital. Now, heat and humidity have been used before. This is in the US. At that point it was a red archive, now this is published. So these guys put them in what are called Rubbermaid dabbas. These are plastic dabbas with tight fitting lids. They were injecting 50 microliters of water controlled with a micro syringe into each of these things. That would, when it was hot, it would guarantee a controlled humidity in the thing. Too complex. It works very well. What we decided is we have a large drying cabinet, a hot cabinet. So this is like you go to a grocery store, you know, where they store these Coke bottles and all in big glass door wala cabinets. Same thing, it's hot. It's at 70 degrees. It's right now at 70 degrees. Okay? It's a hot box. And Tata Memorial Hospital is a cancer hospital. For chemotherapy, most of the patients who come there vomit. They have tons of vomit bags. The stuff you get on the airplane also. They have tons of these vomit bags. So we decided we give all the people in the hospital vomit bags. You write your name on the outside of the bag and you drop your mask inside the bag. These bags come to us in these cardboard boxes. We don't touch your mask, we just put the bags inside the oven, the bags are inside the oven, and then we take them back and it goes back to the section. Okay, we don't have to touch the mask. In this process you have to touch the mask and put it inside the thing. But it's a challenge because you want to make sure that you have to do it in a hospital. Doing it on one mask in the lab and making a process which works in a hospital 3 shifts a day is very, very different. It's something that none of us, I'm just a physicist. My formal training is as an engineering, physics, whatever. I'm not trained to design things like this. But to design things that will work, which department is going to send their masks when? How do we ensure it gets back to the same person? We don't have any possibility of masks getting interchanged. Right? SOPs, because the person handling this is in the sterilization department. I am not there, this is the lockdown, I can't come there to fix anything. What do you do when something goes out of range? So we started this, and in the first wave alone, we decontaminated more than 10,000 masks. And more than 1,500 doctors, nurses, healthcare workers, whatever, they used it. And this, I think, is the first large heat-based decontamination in a real-world system in a real hospital. Okay. So yeah, this was a learning experience. Now, of course, by the way, feel free to ask questions anytime.
There are seed drying devices which are passive, which use the sun. So it's essentially a wooden box with holes on the side, glass top. You keep it out in the sun, temperature goes up to around 60-70 degrees, and because of the holes, humidity is released. Has that been tried?
I mean, if I had access to this in Mumbai, we would have tried it. Just hang on a bit though. So, Tata Memorial is a well-equipped hospital. What about low resource settings? Okay. So this is it. What about low resource settings? Okay. So this is it. What about low resource settings? And that's going to be part 2. Part 1 is interesting. So I was working with Manu Prakash's group at Stanford. Okay. Manu Prakash is the full scope guy. And they were also doing decontamination. He was part of N95 decon, and they were trying to do it in their, this is the experiments in Stanford, where they put the mask in a glass bowl, cover it with something, put that covered glass bowl inside a vessel of hot water and leave it for some time and see what happens. This is what. So we decided, let's do it at home. So here are some experiments done in one of my colleagues' kitchen. So where we boil water in this, we put our mask in another smaller vessel. Again, at this point I am taking data. So I have a temperature sensor on the mask, I have these wires coming into my sensor, etc. And this is, doing experiments in a typical US home kitchen and typical Indian kitchen is very different. Our windows are open, you have wind, it changes every day. This was just before the monsoon season where temperatures are fluctuating. So we put a dupatta around it to try and insulate it, etc. And we got very nice data. Okay, so this is very nice. So the blue curves are the humidity, the red curves are the temperature. So we can maintain it above 70 degrees for 30 minutes, whatever you need to do, and we can do 6 heat cycles. The thing, and this is actually published now. Okay, this is published. Equipment in a paper, I wouldn't believe it. I would never have bet you on this. But you will see what is a journal figure paper. Okay? My point was, why do one mask at a time? Why not do multiple masks at a time? Because in a family it's not one mask, it's 3-4 people. How do you do multiple masks in the same process? Remember, masks mustn't touch each other because I don't know which mask is used how much. So we said, fine, we'll do it. You recognize this? Okay, this is figure in the paper. Okay, so I have actually got my idli cooker in the figure in the paper. Okay, so now, as he said, why not use solar energy? I met a colleague through a friend in ISC who was working with a tribal community in Nandurbar on something called the 100 Sun project. Now the 100 Sun project aims to get mirror concentrators and concentrate heat 100 times so that you can cook. If you want to do masks, this is a very good mask incinerator. At 100 Sun, you can immediately incinerate a mask. So if you want to destroy biomedical waste, it's a good thing to do. But can we use it for mask decon? And we tried it, so I think your trial will work very well. Because we were trying, by the time we got to it, the monsoon was already coming to Maharashtra, so then we went to Ahmedabad to try these experiments. We were doing it in the standard, the standard box solar cooker, the cardboard dabba with wooden dabba with a glass thing. You actually have to open the lid as you go along because you want to make sure that you don't go above 90. You want to keep it below glass transition temperatures of any of the polymers involved. And we actually, really cooked the mask 70 hours, 7:30 a.m. to 5:30 p.m., 7 days just to see which hota hai ki nahi. We also tried a 10x concentrator. This is just a 10x concentrator that also works, keeps up the thing to 70 plus. It's fun sometimes. This is how your typical day looks. This is the temperature. And sometimes you get, when you get some clouds, etc. But sometimes you get, one day we had this very major day. Okay. And this happened to be a day of solar eclipse. So our mask cooker actually tracked the eclipse. Then I tried different things. This is with, this is with a group in Bangladesh actually. So the thing is, what happens when you wash these masks? Okay, I know the charge will go away, but how bad is it? Right? Is it still better than having a typical cloth mask? Okay. By the way, this is a typical cloth mask that has been used for hundreds of years in hospitals. This is double-layered cloth, stitched. You can boil it, you can cook it, you can put it in an autoclave, no problem. This is not too bad. I can give you numbers for this. So, of course, there are many different types of these masks. Some of them are so totally flimsy that you can just look at the light through it and see the difference in the thing. This is 2 layers, this is 3 layers. These are not 2 rupees. These are some of these are. This is like 6 rupees. This is 10 rupees, 11 rupees. So the difference is that layer in the middle. Those were done by people who work on viruses and whatever else in controlled facilities. So there was lots of data on enveloped viruses like SARS-CoV-1 during the first is Hong Kong and something had these flu pandemics and all. So there were similar viruses on which people had worked. Turned out that the SARS-CoV-2 was very similar to that. So people did work on SARS-CoV-2 as well. We are not allowed to work with the virus. Right? We don't have any to work with the virus. So we just believed in the numbers that those guys told us that they said that 65 degrees and 30 minutes is fine. So we said we would do 70 degrees, 75 minutes. Or 70 degrees, 70 minutes, which is like sufficient over thing. The advantage is usually get your mask back the same day. I mean, within a couple of hours. You don't have to wait for 5 days. If you have a shortage of masks and you have to get your mask back tomorrow, this is one way to do it. So what happens when you these masks? We actually measured the charge on them. We measured the filtration efficiency. Wise, whatever material that was shown there, this is the same thing. Okay, this is exactly the same thing. It's just the shape that is different. The amount of material is different. The filtration efficiency is pretty much the same as of N95. It's just that the design is different. Now, I washed it. This is all stuff in the lab. And we wanted to wash it with the cheapest way possible. So you buy the most sasta detergent tikkiya that you get and scrub it because that's the way people would probably wash it. Put it out to dry. This was hanging in the lab to dry. We did this, and this was because in Bangladesh there was a randomized control trial to be done on 350,000 people. 350,000 people trial to see what affects mask usage. So does it matter if I distribute masks for free at a grocery shop? Does it matter if the imam in the mosque tells people please use these masks? And of course, we want people to use the mask multiple times. So one part of the study used cloth masks, one part of the study used these masks, and people wanted to know what happens when people wash these masks. And the thing is, it is okay. I mean, you know, it goes down from this to about 80%, but 80% is still a lot better than this one. At 0.3 micron, this is hardly 50-60%. Okay, so this is not bad. Even after 10 washes, 80% is not bad.
What do you mean by charge?
What do I mean by charge? By charge, I mean electrostatic charge. So effectively what we do is we have a P3 electrometer, keep it on it and see what it's like a capacitor measurement of how much charge there is. So these are actually SEM images. You can see the outer layer. Don't worry about this. These things are just when they stamp the mask together. There is a process called calendering in textile fabrication where they push these. These are all non-wovens. These are all non-woven fabrics. They stick them together by heating it up, and this is the mark caused by that. These are, you can see, this is 200 microns. So these are very fat and open fibers. This is the middle layer which has this very thin fibers. Okay, and this is again the inner layer which is quite loose. And nothing happens. You can see the difference after 5 heat cycles and 3 wash cycles looks pretty much the same. So you don't do much. You can't see the charge going over, of course, in an SEM. And we also did some, interesting science. Now, if the problem is with charge, can you recharge a mask? Can I put the charge back? And we thought, okay, let's try something. We'll just do a very simple capacitive thing. We just put 2 metal plates, put the mask in the middle, and put a high voltage to it. Okay, and see whether we can put back charge it somehow. Put it in electric field. And this is a new N95. You wash it, it becomes 75%. You put it back after 8 hours, it's back to 95%. Hey, wait. How do you charge it? You need pretty high voltage to get a significant field. Pandemic. Right? How do you get a high voltage source? Mosquito bat. This thing you use to kill mosquitoes. Those have a high voltage source inside. You need voltage, you don't need current. Right? So you open up some of these mosquito bats and use their high voltage source. Okay. So then we thought we can make something which is a continuously rechargeable mask. So we made this is fun, right? TIFR, come on, we have facilities. This is a 3D printed plastic thing with an enclosure with a metal gauze between we cut out fabrics from the N95, put it between 2 metal gauze, connected it to a battery. But the point is, nobody wants, see the point, it's perfectly safe. There's no current in it, right? It's only voltage. But you tell people you have a 2000 volt thing, they say, nahi baba. Okay. So I don't think this is commercially viable, but theek hai, we could get a big one. Yeah, this is not for, this was a fun experiment to try. I'm telling you, forget cost, even if you give it free, nobody will take it. You tell them 2000 volt battery hai piche, nobody will take it. And even if it's powered by a single 1.5 volt cell or something, but finally it's a voltage multiplier. So
what if you tell also that it's same as a mosquito bat? Even worse.
Even worse, yeah. वो मच्छर मर जाता है उसमें. Now finally I'll tell you a bit about UV.
But the charging in masks is inherent in the chemistry, like we don't in the new mask. It is inherent in the chemical process.
No, it's charged. Corona is charged. Corona charged. They do put in electrets in it, which are permanently like a dipole, an electric dipole, which is permanent. So they mix. There are people mixing these days, mixing magnesium stearate and lots of other chemicals. They mix with the polymer, which allows it to store the charge metal. So there is lots of patents and all on this. But yes, it is. Then eventually it is. So they either the way you generate these polymers is you have a melt and then you electrospray. So while you're spraying the melt is extruded through very fine nozzles to generate those fine fibers and collected on a roller on the other side. And you put a many kilovolt difference between the things, so it gets charged in this process. Or after this fabric is made on the roller, you come to the corona discharge and you go over it to charge it. That's how they make these charge things. Okay, finally, if I have a few more minutes, a little bit about ultraviolet light. Ultraviolet light, UVC, has been used a lot, and there's been a lot of hype about this. And unfortunately, once I got into this game of masks, everybody starts sending me UV dabbas for me to comment on them. And there are some very basic physics that people get wrong. So, right now, the cheapest source of UV light, that is rupees per watt, joule, whatever you call it, of light in the UV is still a tube light. The UV tube light, basically, which is the same as a normal tube light, you don't have the phosphor coating. But that tube light also, when you get a Philips 11 watt or something, 11 watt has a total power consumption. Mercury has many lines, only some of them are in the UV. So a 10 watt tube light puts only 2.5, 25% is what you will get in the UV. People just assume that because I have an 11 watt tube light, I am getting 11 watts of UV. That's not correct. Okay. The other problem is, everybody wants to make their dabba look nice and shiny. So people are selling on the dabba ki fruit dalo, vegetable dalo, sab kuch decontaminate karo. Okay. They make nice stainless steel dabbas. Stainless steel is a very poor UV reflector. It's the worst choice you could make. I'll show you in a bit. Then UV does not penetrate very much. Now the thing is, if you have a mask, the virus, if you want to get rid of it, is not trapped on the outside of this, it is trapped inside the lid. So you have to get enough UV intensity inside, which is why you need a surface intensity of almost 1 joule per centimeter square. That's the amount of energy you need to ensure that you got rid of whatever you want to do. To get that with standard light sources and something you can, and people also forget the inverse square law. They made a big dabba, we put so many tube lights, so we assume so many watts are there. And because that tube light is there, it's not coming on your sample. There's something called inverse square law. So there are most people make complete mistakes in this thing. You have to be very careful because if you have a lot of UV below 200 nanometers, you generate ozone, which is good for decontamination. Ozone will help you burn up once it's something, but ozone is not good for you or the people around, and you can smell it. And these UV lamps operate with it's a very sort of smells like the seaside. That's all I can say.
You won't know it in the moment.
Yeah, I mean, but otherwise you will still know it inside the room because inside the room it doesn't smell like the seaside. It smells like the seaside. Then I have this ozone thing. And of course, the problem is if you have a strap, the shadow of the strap will come on your mask. There's no decontamination happening below that. Okay. UV also damages plastics and polymers, so you have to be very careful with this. And there are many things. So this is something that we were trying. We were actually we collaborating with the company. It's like a microwave sized dabba. It's basically an old microwave dabba, which has been converted to it, and we put aluminium foil. Aluminium is a reasonable reflector. We have multiple lamps. These are the lamp fittings, the tube light fittings, top and the bottom. And at least we can get 1 joule in about 10 minutes, which is okay. 10 minutes is better than the 70 minutes I need for my thing. But the problem is shadowing and all this stuff. But I did enter into a collaboration which was really a worldwide collaboration. I mean, many of these international collaborations I've had with people in Germany, people in the US, something like this. But this was a collaboration with, and it was fun. It was amazing to work with people in Peru, people in Africa, people in everybody trying to design something. We designed this UV boxes. Again, this is a paper based on this collaboration, and I think we should leave time for questions. Masks work. If you wear it correctly, it's the easiest thing. The easiest non-pharmaceutical intervention that you can have is wear a mask. And we of course built this thing, and this told us that not all masks are the same quality. The quality is not determined primarily by the thing. I'm going to pass this mask around. Okay, tell me what's wrong with this after you pass it around. Don't wear it; it's very dirty, but you figure it out. And there is a huge proliferation of poor quality masks in the market. Huge proliferation of masks. Okay, and I actually worked with a journalist to try and. So what happened was everybody was in a rush to make masks. Okay, and what they do is sometimes they have the right materials. They're getting the right materials. But if you look at these masks, these edges are fused. They're heat fused. Okay, you can take the best quality mask. Then if you decide to stitch it, your needle is making holes in it. That's the end of it. It's no longer N95. You've got holes in it made by needle. What else do you want? Okay, so these are things which people in a hurry never realize. They were giving the data of their filtration efficiency, but the mask they are making, and if you have a mask like this, if this side is stitched, that's the end of it. Everything is leaking through that. It's not much of a mask. So we did a lot of interesting experiments with that. N95 masks can be decontaminated and reused, and I think this is something we should do, even in times of plenty. Right now there's no dearth of masks, but just remember, if you use this only once, what is the amount of non-biodegradable waste that we are generating just because of the amount of masks we use and throw? If you use the mask at least 5 times or 10 times, you would reduce the amount of junk we create. And I think that is one good reason to recycle masks. Forget COVID, just for this. And I think you can wash masks a few times. They're probably worth washing. I've had a lot of fun with masks in the last few years, and I hope I could share some of it with you. You can ask me questions, and there are some otherwise interesting stories I can share about how luck plays a role in many of these things, and how I landed up being just at the right time, having my phone in my hand, otherwise things would have never happened, the story would have never been told. How I managed to connect with this journalist who was looking at masks and could get me the data. You know, there was a tender for masks somewhere in Delhi, and they found that 70% of the people who applied, the certificates were fake. Okay, so there are a lot of things that I've learned. Valve masks, these masks which have valves, you saw one where I was using it. Why they are a terrible idea, I can tell you how we petitioned the government to try and get rid of them. So I've had my share of fun in the last few years. Thank you. But finally, remember, the best mask doesn't help because that's how we wear masks in India.
And I think we can open for questions for some time. Anybody has any questions?
Yeah, go ahead, Prof.
So recently, the mask has a layer of charge in the middle, right?
The middle layer is charged. I mean, you don't have a layer of charge by itself. The charge is attached to the fabric. The fabric is charged.
How exactly does it help in filtering the mask?
So you have a droplet. If there's an electric field, the droplet will get polarized. One end will be positive, one end will be negative, and then you get attracted. It's the electrophoretic effect.
So it passes through.
Yeah. So it's passing. I mean, it passes through, but there is enough time for this. These things happen on a very small time. Very quick time. There's charge and there's trap. Remember the what looks like to use a layer. I can show you a 3D view of it. It's actually a very, you know, that you saw the thing going on. It's quite thick. Even if it's 1/10 of a millimeter thick, for a 300 nanometer particle, it's a big forest through which it's going. Right? It will get trapped.
So it gets trapped in the layer.
Somewhere in the mesh. I can show you how it actually looks if I show it at 2 scale. There is some simulation.
So when you had monsoons in Maharashtra, what took you to Ahmedabad?
I didn't go.
No, I mean, what was the reason behind Ahmedabad being picked? Was it the first one? What was the other reason?
Well, he works in this low-cost technology business, etc. And I think I am Ahmedabad. There's some foundation there that supports all this, so he knew people there who would host him and he went to Ahmedabad.
It doesn't really
It doesn't rain much. Also, that's one of the reasons that he would get some more time, because by the middle of June in Mumbai it's already getting cloudy and it's difficult to get sun.
How did you get that idea of using PMM counter for atmosphere? CPM counter.
Okay, so I get this thing from the hospital saying that do something. And I start looking around how we measure filtration efficiency, and I figure out that you've got to get a particle counter. The first thing we did was I went to our clean room. We have a clean room for the microelectronic fabrication, and we measure the air quality of the clean room. There's a meter that measures it. I brought that meter, and this meter measures particles. It gives me the range of particles of from 0.3 micron to 0.1 micron to 10 micron. It gives me a distribution of particles, and we said, fine, we can do this. So what we are doing is eventually we moved to that chip, but we were measuring different room air, hanky, t-shirt, clean room wipes, surgical mask, whatever we could lay on there, just trying to measure it, holding it on top of that particle counter, and say, yes, this works. So then I joined this group called N95 Decon. So I sent Manu Prakash an email, Thursday 9th April, 6:23 in the morning. Okay? It's still evening in California. 6:34. I send the mail at 6:23. 6:34, the guy replies saying that we can include you in the community ASAP, we can talk more tonight, etc. 6:39, somebody has added us to the group. There's a meeting that evening, attend that meeting. In that meeting, the head of the optics department in Stanford tells me that, you know, a lot of people in California, there are these wildfires happening, they have bought these sensors. Okay, there's a Chinese company that makes them. Lantau, you can get the sensor, which is that chip that we need. So now, then I try to find out this thing. By 7:53 we are on the thing, and then I get this call, and luckily I'm on WhatsApp. This thing is at 9:34 a.m. saying, can we have a Zoom meeting at 10 a.m. We had a Zoom meeting at 10 a.m. And now I need a particle counter. This is how I got the idea from this, talking to these people in the earlier evening. I'm looking at all the suppliers in Mumbai who can supply electronics. The standard place to buy electronics, Hamilton Road is closed. The standard place to buy electrical equipment, Sabha is closed. What do we do? So I look at all pollution monitoring people and start cold calling them. Right? Do you have a pollution monitor for me? I'll buy it, I'll use the chip of it, I'll do something to it. The fourth guy I called, is this dude, Ronak Sutaria, Respire and Living Sciences. He says, are you Arnab from China? Yeah, I know you. Tell me what you want. Okay? So he has this sensors, he's into air quality monitoring. So after lunch, I arranged for this curfew pass, TIFR, government has to arrange for a curfew pass, got a vehicle, went to his house, took him out of his house, take him to his factory, get him to open his factory, get us these chips and come to TIFR, and we worked on it through the night and we sort of figured out what to do. Okay. So it is thanks to randomly being able to get ideas from people, meet people, get the right people and get your chip. So he didn't have these chips, he makes pollution monitoring equipment like this. Initially we were using his dabba, but his dabba has too many leaks in it for it to be really useful. It's good for monitoring general air quality. So we actually opened his dabba and took the chips out. Eventually, much later on, we could order chips from Amazon and all after the thing got done. But this is how it started. So that's how actually things started. Yeah. Any other questions? It's gone again. Let's not worry about this. Yeah. Very good question. So if you see a good quality mask, it comes inside a sealed plastic bag. And one of the reasons for the sealed plastic bag is to protect it from environmental humidity. Now if you use a mask for 8 hours, the humidity in your breath will start discharging it. Okay. So there is a problem with these masks are actually very difficult to use for very long. Especially in very humid in monsoons and all, we find that it does get discharged quicker than otherwise. But it's still, see, the thing is, even what you can get, remember that everything is probability, right? One viral particle is unlikely to give you COVID. You need a minimum dose before you will get COVID. Hence, even a cloth thing that removes 60% of your things is worth it. And remember that mostly it is not the 300 nanometer particle. This stuff is very good for droplets. If you, as long as you're wearing a dupatta, a handkerchief, a old t-shirt, whatever, which is cutting out droplets, you have removed most of your worries about viral particles. You don't worry about the 300 nanometer size. Unless you're in a very crowded environment, there are lots of generation of things happening where, even the stuff going through is going to be significant. People have shown that also, that in a crowded bus you can have a problem. There was a Chinese incident, one guy with COVID here, everybody in bus, in spite of people wearing, at least in those days, simple masks. But masks work.
So, we have often...
No, it's fine. I think you had a question.
We have been using CO2 monitors in indoor situations to monitor lack of ventilation.
Yes.
Or ventilation.
Yes.
How well do they work?
Absolutely. That is probably the best way to do it, is to, we've tried this with a fire extinguisher and a CO2 monitor. You give a pulse of CO2 with a fire extinguisher and you see the decay curve. That tells you what is the air changes per hour effectively that you're getting for a certain volume. In fact, the worst thing is closed spaces. As long as you have open windows, etc., the ventilation. See, outside, the outside is like, so much dilution that you don't have to worry about it. Diffusion takes care of it. What you need to worry about is closed spaces, train compartments with windows closed, cars with windows closed. Those are probably the worst places you encounter, where you don't have, remember, the standard split AC does not give you any fresh air. It's only a recirculating thing, right? Unless it has a filter that is trapping things, etc., it's not really giving you any protection. You need the best. After masks, the next thing is ventilation. And ventilation is something that has never been considered properly in the design of most buildings, because we just assume thanda hai to theek hai, AC.
We have 4 large exhaust fans in this room, which are used when the class is full. We deployed them during the end semester exams last May, April, May, for the first time we had 100 plus people sitting in a room. And we use CO to monitor them.
I think see that's the standard way to go. In fact, the companies will do a ventilation audit for you, which basically what they do is spray some carbon dioxide and see how long it takes to go away. You can do alcohol and other things as well, CO2 things. And the most relevant.
Could you please elaborate as to why masks with balls are bad idea?
Yes, certainly. The valve is something like this, which has a sheet of rubber, okay, which can open out when you blow out, and when you suck in, it seals against the thing. So it has zero resistance on the way out, effectively. For COVID, you want to protect the environment, the people around, from somebody who is releasing a virus. It is not good to have a zero resistance path on the way out. It defeats the purpose of a mask for viral infections. So this is one thing. The other thing is, if you are in a place like Mumbai, which is humid, you breathe in and out of a wired mask for an hour. The mask, that rubber gasket, is going to get humid. After that, a speck of dust sits on that humid gasket. It's never going to seal again. And then you don't have an N95 mask also on the way in. And I have got measurements. So, here you see this is the 0.3 micron thing. You are getting the sides, we are taping it, we are putting sellotape on the side to sort of tighten it, and it's still only around 75%. Okay? This is the first thing, that this is a new mask. The new mask, you do it like this, it's around 90%. Forget, this is not, I have not done any calibration or anything. So assume this is 95%. Okay? And whether it is open or taped, it doesn't matter. But after you use your mask, if the exhalation valve is there, it's 75%. If I take that valve shut, it's back to 90%. So the leakage is through the valve. So after you use these masks in humid atmospheres, they do attract dust and then they don't seal at all. And then that is a problem if you're really using it in a, if you're working with COVID patients in a hospital, you don't want to be using that mask. So valves can be very leaky. That's the answer. Yes, we did. So the first MOHFW thing allowed wired masks to be used. And then eventually many of us across the country wrote to the government saying that this is not a good idea, this was meant for something else. Please stop this, and then they stopped it. Took away. The lady in the back had a hand up.
We have been seeing accesses and all, and we are putting them after multi-layer. But didn't you see any problem breathing if you put a multi-layer thing? Even if you put a dupatta in front of our nose, we feel the breathing problem. So multi-layer mask would be a way to follow the that.
Would I run a marathon in a mask? No, I would not. Okay. Would I, if it is a good mask, okay, masks have to have a certain maximum possible pressure differential per area for a given mask. Masks that meet it are actually very comfortable to use. But again, there are a lot of masks. In fact, the one, I was passing around a mask, did you notice that the straps were crossed?
Yeah. Yes.
Right? It's strap, the strap here doesn't go, the upper strap goes niche here, and it's impossible to, So this is what happens if you don't have quality. All the masks you get, 10 rupees you can buy a mask on the road. BT Subway ke bahar in Mumbai, you're getting masks for 10 rupees. These are all the masks which are rejects from some place, country not to be told, but they are available for 10 rupees. Now the problem is this, if I complain against it, the poor guy who is making a living and probably gets 50 paise out of every mask, he said that the police will catch him. My thing is at least ठीक है यार, जो भी mask है 50% is better than not wearing a mask, चलो यार पहनो, But finally these are all reject masks. which are there, which have all these interesting defects in them. These masks will not satisfy your breathability thing at all, because people don't measure this. This is my filtration, etc. But if a mask is good, it is typically breathable. Any cloth, you take a dupatta more than 3 times, you're going to create some. You will always create a resistance. You are adding a resistance to airflow, right? So it is going to increase the difficulty by some amount, definitely. No question. I'm not questioning that. You're putting another resistive element, right? But is it such that it impairs normal activity? I would say no for a good mask or even a dupatta. If you want to do exercise, if you're doing sort of heavy breathing, obviously it's going to become a thing. Does a mask affect? Mask में carbon dioxide बढ़ जाता है. I'm sorry, I mean, look at the size of a carbon dioxide molecule versus something, right? That is not a. What happens is it gets more difficult to breathe. I would agree. Under heavy breathing, you go on a treadmill and make measurements with the mask. That's because your overall output is of CO2 or something is changing. I don't think it's basically, if you have a well-designed mask within the pressure parameter threshold, it should not be a problem for normal activity. Let's put it that way.
So you talked about working in low resource versus high resource environment. What is your major takeaway in working in a low resource environment? Would you have preferred working in a high resource environment? Would you have gotten your data faster?
Come to my talk at 4 o'clock. We'll do much more on this at 4 o'clock. No. I think, would I have got my data faster? Certainly. I mean, see, you guys are all IISER students. I teach experimental methods in TIFR, course that I've taught many times. Finally, there are only 2 things in the world you can measure: voltage and current. Right? Whether you measure temperature, whether you measure magnetic field, whether you measure current, whatever it is. I mean, at the end of it, you have a transducer that converts it into voltage and current, which I can then save in my computer and I can work on that data. If I have transducers for everything, it makes life simple. If I don't have transducers and I have to take data by hand, etc., it's obviously a slower process. I was lucky that I had transducers in the development in the lab, right? But at the end of it, you want to design processes where you're not limited by having transducers. Faster, certainly, but sometimes I think it is much more fun to face a challenge of how do I do it without having this. Can I have a proxy for the measurement which tells me, I have a Bosch makes these differential pressure sensors. I can put a differential pressure sensor connected to, even if I don't have a readout for it, I can connect it to a multimeter and read the voltages, put a 5-volt supply from somewhere, USB 5-volt from a phone charger, put it to your sensor, read the voltage on a multimeter, and get some idea of what I have some numbers, I don't know what the Pascal value is, but I have some numbers. Okay. On the other hand, once I do it for a set of masks, and then I see that, look, if I hold the mask up to the light, hold these 2 masks up to the light, you can tell me the pressure differential by looking at it. Look at a bulb split. Farak dikhta hai na? So now I can look at a window, I can look at something. This tells me that if I can see the reflection of the tube light on the table through the mask, let's not even measure this, look at it. So sometimes you come up with proxies for measuring something, which I think part of the fun is figuring out, oh, cool, I can use this to do it even if I don't have a sensor. So I have actually, the idli cooker was such an aha experience. It's like, it just suddenly occurred, hey, let's do this. I don't know if you were in a lab and something would have probably over-designed the problem and come up with something we could put stack 5 masks with. I was thinking of using पुराने ज़माने में CDs and DVDs used to come in this tower of 100, right? So we have some of the old things lying around. So we could maybe use some of those things. See, that's also plastic. वो पिघल गया तो problem है, your temperature is too high. That. So things like, I don't know. I deposit materials by semiconductor materials in an epitaxial process. I deposit atoms layer by layer. I have my growth apparatus can deposit a single layer of gallium atoms and a single layer of arsenic atoms or something. On one end, I work on the extreme high end tech end of things, where I have control to deposit an atomic layer and see that. I can see that in the polarization anisotropy spectrum or something, and that's exactly one of their values. Okay, that's one end of stuff which is also exciting. But I think it's also challenging and exciting to work with severe constraints where you don't have any stuff and you just need to get stuff done.
Right. Thanks a lot, Professor, for taking your time to give us this talk.
And just write to me if you have any questions.
Sure, we'll have to do that too. And I thank you all for attending this talk.